doing TLC. I can't remember what. Whatever's listed though. Okay, which ones are tautomers of the one in the box? Tautomers. Well, the first three are tautomers of the one in the box, yeah? How do we do? First three are tautomers of the one in the box. This would be a OH tautomer. That's an OH tautomer. This is actually a CH tautomer. Yeah? How we do on these? That's not a tautomer. For one reason, it doesn't even have the same formula. Are the following tautomers? Yes, they are. The difference between these two, relocation of a single hydrogen, and then at least one or more pi bonds. Yes, they're tautomers. Any questions about those? Last question at the bottom. Tautomers are more broadly called what? Yes, constitutional isomers. Okay? They're none of these. They're definitely not resonance structures. Whenever we start doing resonance, and we've already done it, whenever you do resonance, you don't move any atoms. Atoms are not moved when you draw resonance structures. Tautomers, you relocate, you move a single hydrogen, so it's definitely not a resonance structure. This constitutes two constitutional isomers. Those two molecules at the bottom are constitutional isomers. Same formula, different connectivity. And that's it. Any questions about tautomers? At the top here, what type of product did we make at the top? When this thing tautomerized, what was the product? Hold that one. Double bond ends up being between the oxygen, right? We could do some other type of tautomer, another CH tautomer. No, well, hold on. This is an OH tautomer. Any other tautomer of that would be a CH tautomer. So I reckon the only one is going to be here. Let's move the H here. Double bond becomes between the C and the O because when you tautomerize enols, you typically get carbonyl compounds. Here's your carbonyl compound. What type of functional group is that? That's it. To me it looks naked. It's an aldehyde, but I like to draw in the H's on my aldehyde. Most people do. What have we done? We relocated this H to where? To here. There's now two H's there. Second carbon now has two H's, where the second carbon here only had one. And we moved the pi bond to be between the C and the O. Yeah. If you think about it, you don't really need to think about it. If you do the chemistry, yeah, it's an aldehyde. But if you do this reaction with a terminal alkyne, you're going to end up with an aldehyde. Okay? But that's nothing to memorize. I mean, everybody knows that's an aldehyde, right? How do we do on those? Okay, reduction of alkynes. Take an alkyne with two pi bonds. We can hydrogenate the pi bonds. Hydrogen and a precious metal catalyst such as nickel, platinum, palladium. We've looked at this before. And you could add two H's across the pi bond. How are the H's added? Are they added in syn or anti-matter? Syn meaning is essentially the same thing as cis, but syn is more when you talk about how things are occurring. Syn or anti-addition of hydrogen? Syn addition, right? Comes from the metal, same side? Yes. So if we add two H's on the same side, we're going to get this. If you want to draw in your H's, they're going to be on the same side. Thus, the alkene here will be cis. The two major groups will be cis because the two H's are cis. Right here, this is linear, but once we make other bonds, these become trigonoplanar, and now we've got cis or trans possibility, but the intermediate is going to be cis. But the intermediate still contains a pi bond, and we know alkenes can react with hydrogen, so this can react again. And when we react it again, this becomes an alkane. Now that has free rotation, and there is no stereochemistry in that particular product. And ultimately, we're reacting this and going here with hydrogen, two equivalents, two molar equivalents, and some type of catalyst. It's very difficult to stop here at the alkene stage because these will just keep reacting. They'll react again with your. So I put brackets around it, usually not isolated. But we can still show it and understand this is the intermediate, not a mechanism intermediate, but a true intermediate, but it's not isolated. So it's sort of like a double hydrogenation or a full hydrogenation, a complete hydrogenation of the alkyne to the alkane. That's a shame because the alkane, there's pi bonds and all sorts of reactivity. So sometimes you may want to make alkanes. There's an example in the handout. So just twice the fun. Now, can we stop at the cis alkene? Well, chemists have developed a way to do that. If you use a so-called poisoned catalyst, if you use a poisoned catalyst, you can stop at the cis alkene. And actually, if you use a poison catalyst, it just will not continue on, if you're lucky in most cases. Exceptions to everything. But generally, it stops here and it won't even react again. The poison catalyst will only allow it to react with the first pi bond of the alkyne, but it won't react with the alkene. What's a poison catalyst? Poison catalyst is still going to be something like palladium, precious metal, but usually something's added to it to make it poison, to make it less potent of a catalyst. Sometimes heavy metals like barium sulfate or lead sulfate. You might even have something else like an amine. And amines will coordinate with that palladium. Okay? Palladium surface. In the end, one of these mixtures of three things is called Lindlar's catalyst. Whenever you see Lindlar's catalyst, it's the most common example of a poisoned catalyst. Probably palladium and one of these salts, and probably also like quinoline. It's a mixture of things that leads to a poison catalyst. So you may see it like this. If you see something added, that's probably often a poison or like a dopant or Lindlar's catalyst. Poison. Use a poison catalyst to stop at the cis alkene. Reaction will not continue on. This implies that hydrogenation of the first pi bond is easier and hydrogenation of the second is more difficult. And that is indeed the case. Because if you think about it, if the first hydrogenation was difficult and the next one was easier, then why would it only do the first one if the next one's easier? Well, it doesn't, because actually the first one is easier. And so these will do the first one, but the more difficult one it won't do. Okay? And if you want more information, well, you have to look into it. Importantly, though, anytime you do a hydrogenation, it's a syn addition, right? Okay. What about a transalkene? Can we convert an alkyne to a transalkene? You can't do it with hydrogenation because that syn addition is going to give us this alkene. Well, you can, but it's a very different reaction. And it's actually our first look at a radical reaction. You can do this using sodium metal. Okay? There's no ion here. It's sodium metal, sometimes clarified by writing oxidation state of 0 above the metal. And ammonia. And in this case, ammonia is used as a solvent. If you take ammonia gas and cool it down to minus 33 degrees, the ammonia gas will become a liquid. You can actually use that liquid as a solvent. Okay? You know, I sent a video yesterday about the lower thing, the lantern. I should have sent a video about this. Actually, when you add sodium to ammonia, it turns a beautiful blue color. Okay, color this jacket over here. What's going on there? What's the mechanism for this reaction? And why is it trans? Why is it called a dissolving metal reduction? Is it a reduction? What's going on here? What have we added to this molecule to get this one? What's the difference in formula? 2 H's have been added. So look at it, 2 H's have been added in an anti-manner. When you add H's, that's known as a what? Reduction. Right? Okay, let's look at this mechanism. First off, if you take sodium and put it in ammonia, we have sodium in ammonia, you're going to get, what does sodium like to do? What does it like to give up? What does it like to produce or give you? It likes to give you electrons because it likes to give up one electron and become sodium plus, which takes on the electronic nature of neon. All right? It likes to give up electrons. It will actually give up its electron to the ammonia. But it's how does it do this? It's actually considered or called a free electron. We'll get electrons plus sodium ions. And this is a little bit sort of vague, like what's going on here? And this is called a solvated electron. And the best theory that we, scientists, us, can come up with is that the ammonia is sort of solvating it, sort of like hydrogen bonding type of thing, or, okay? Because it's in equilibrium. And if you just let the ammonia evaporate, everything just goes back to this. So it's sort of this equilibrium solvated state. Okay, again, there's more you can look into this. The amazing thing about this, it turns blue. Why does it turn blue? It's another amazing thing. But here we go, solvated electrons. Usually we have something with a lone pair. 2 electrons on an atom. Here we just got 1 electron. Is it free? I don't know. Okay, but it's an electron. I'm just going to call it like this. This electron then reacts with the pi bond. Now every reaction we've done, pi bond attacks something. Pi bond is the nucleophile. It attacks. But it's not going to attack electrons. These electrons are not going to attack electrons. The other way looks like too. Here we go. Let's just do it, then we can step back and assess it. One of these electrons adds into the pi bond, pi system, like this. Boom. Whenever you move a single electron, we use a fishhook arrow. I think this was in my guidelines to mechanisms. By the way, when I give you guidelines to mechanisms, I don't give you all million things. I give you the things that are critically important. Everything in my guidelines to mechanisms are things we got to know. All right? I don't give you stuff that is just extra fluff. I give you the stuff that makes it so you can succeed. I don't think it's critically important, I'm probably not going to give it to you. All right, we pump that in there, okay? We got to just go with this, but we're going to move these two over. Now, can you follow that? What does that arrow movement give? Well, we got 4 carbons. I'm going to draw it. I'm going to draw a trans. What's now on this carbon that just got pumped in? An electron. Now I'm going to draw it as a dot. Can I do that? I mean, here I did it 2 dots. It's 2 electrons. 1 electron. What's on this carbon, though, as indicated by this arrow? The pi bond moved over onto that carbon and became a lone pair. What are the charges now? All right, what's the charge of this carbon now? Yes, it's minus. Everybody can do charge, right? What's the charge of this carbon? Neutral. It's neutral. That carbon owns 4 electrons. It's supposed to own 4. By the way, what's the charge of an electron? Negative. And if you add a negative to a neutral molecule, the resulting should be negative. Right? Well, it is negative now. We added 1 electron. Okay. Why is it trans? Right there. Because I could have drawn this cis. Could I not have drawn that also cis? Which one's better? It's trans. Here, the molecule has a choice. And it chooses trans because the transition state leading to this is going to be lower because it's a lower energy molecule. It has a choice here. That's why it's trans. When you do a hydrogenation, the molecule doesn't have a choice. It has to be a certain way because the H is coming from one side. Here it has a choice. Okay? Now, what do we got to get on this molecule to get at the end? We said it earlier. H's. Where are the H's going to come from? The only source of H's in this reaction is the ammonia, right? The H's come from the ammonia. This is a very strong base. It's a carbanion. Carbon doesn't like being minus. We'll see carbanions. Very strong bases, though. It will actually take an H from... In Gen Chem, you learned ammonia is an acid or a base. And in 3rd grade, what did you learn? Base, right? Ammonia's a base? You know that too much. But you just memorize that, you don't understand why it's a base. But guess what? Let me blow your mind. Right now it's going to act as an acid. You ever seen ammonia act as an acid? Right here. These electrons take an H from ammonia. And what does this give? This is our good old acid-base mechanism that we introduced 6 weeks ago at least. Right? Right, you had arrows. What does this give? Boom. What's now bonded to this carbon? An H. Plus what? What did we produce over here? Nitrogen with an H and an H. How many lone pairs on the nitrogen now? 1 originally, 1 now from the acid-base reaction. This is a minus charge. Let's don't forget our over here. By the way, what do you call something with a single electron? A radical. Okay? single unpaired electron. It's called a radical. What do we do next? Well, we actually need another electron. Take another electron, and it gets pumped in here. Because if we've got a free electron floating around, electrons do like to pair up. I mean, that's why you have bonds, because you have your electron pairs. So we get another one coming in here, and that leads to what? Boom, boom, boom. H here. Now we have a lone pair there, and that's a minus charge. How do we get final product from there? What do we need? We need another ammonia. And these electrons now take the H, and we get that, and we make another NH2 minus. How does that mechanism look? Reasonable? No longer magic? We can understand. This is the leading theory of how this reaction occurs. How much has been proven? Most of the mechanisms we looked at have been studied very much, and they pretty much have been proven as much as they can. A variety of ways you can prove mechanisms. Is everybody convinced that that mechanism gives that product? How we get those two H's there? Okay. Well, let me ask you this. What else is formed here if we balance this out? We get this plus what? What else would we show over here? Two what? Okay. Because yes. If we fully balance it. Let's start over here. Let's fully balance it. One of these, how many ammonias did we need in this reaction? 2. The ammonia supplied a proton here, and then we needed another ammonia to supply another proton. 2 ammonias. How many sodiums did we need in this reaction? Each sodium gives 1 electron. So we need 1 electron, but then where did this other electron come from? The second sodium. We need 2 equivalents of sodium. What did we make? What did we show over here? First off, we made, does everybody agree we made sodium ions? Because each time sodium gives up an electron, it becomes a sodium ion. How many sodium ions did we make? 2. And what else did we make? We made this guy. How many of those did we make? 2. 2 NH2 minuses. Now look here, we got a plus and a minus. Okay, blow your mind here. We could have just shown this as what? 2 NH2. Just show it like that. Just like if we have 2 sodiums and 2 chlorides, doesn't this equal 2 sodium chlorides? Right? I'm just showing the sort of like formula, right? Of course, if you see this, you know this is ionic, right? Sodium's always ionic. So this is positive sodiums and negative nitrogens. Okay? So it's completely balanced. 1, 2, 2 gives 1, 2, 2. Why is it called a dissolving metal reduction? Because we start with a metal, and most metals are not soluble in anything. Of course, when you add this to ammonia, it dissolves. And then the reaction takes place. And at the end, all this is dissolved in the ammonia. So we start with the metal, and now everything's dissolved. And so it's called a dissolving metal reduction, and it's quite simple. That's where the name comes from. A lot of metal reductions are dissolving metal reductions because the metal is dissolved at the end. Sodium is a metal. The metal is the reducing agent. The sodium gets oxidized. Sodium is now oxidized. What got reduced? the organic compound. Okay, that's our first look at a radical reaction using a fishhook or a half arrow. Questions about that? It'd be good to look at a video of that. I think there's a good video out there of somebody doing the reaction. Also, if you remove the ammonia, how the color fades, etc. Let's look down here and then we'll see what we can talk about. Okay. So, how do you get a trans alkene from an alkyne? That we just did, which is what? The dissolving metal reduction with sodium and ammonia. By the way, you can also use potassium or lithium, but sodium I think is most common. Lithium is less reactive. Potassium is more reactive. Amazing reaction though. Amazing reaction. Color, using ammonia as a solvent. Solvated electrons. Okay, last topic for alkynes is looking at the acidity of terminal alkynes. Back when we looked at acid-base chemistry, test 1, we talked about hybridization, and we mentioned that terminal alkyne, the CH, has some acidity. pK is about 25. Somewhat slightly acidic, enough acidity that we can do something with it. Okay? It requires a very strong base, though, to deprotonate this. N-butyllithium is a very common strong base. N-butyl, straight butyl, with the N-carbon being a carbanion. So carbanions up there. What do we say about them? Very strong bases. I mean, this will take an H from ammonia. It also will take this H here. And then lithium is the cation. That's a very common N-butyl lithium. These electrons take the H. These electrons stay behind. And that would give this lone pair like this, carbanion, carbon anion. And the lithium can sit with this, but then this becomes butane once it takes an H. Which side's favored? Well, this is 25. Butane is not acidic. It's greater than 40. That's why this is such a strong base. Which side's favored? Weaker acid, right? This side's favored. By how much? By at least what? By at least 10 to the 15. That's what, 100 gazillion? So at equilibrium, you got 100 gazillion of these and only one of these. It's pretty much complete. That's 99.9999999%. Pretty much complete. N-butyl lithium will deprotonate the terminal alkyne to form the carbanion. What's the name for the carbanion? Alkynide, like an alkyne anion, like a chloride. You don't see that term used much. More often it's called an acetylide anion. Acetylene being the simplest alkyne. All right? So a lot of times you just call this an acetylide anion. These can be formed using such a base. You can also form these with NaNH2, which, by the way, we produced in the above reaction, right? As a byproduct. Okay. This is also, I mean, you can buy this. It's a base. We know this is sodium plus, right? We just looked at this. NH2 minus. I mean, this is stronger than ammonia, right? Ammonia is a neutral nitrogen. This is a negative nitrogen. That's even stronger than ammonia. This is called sodium amide. What's an amide? Ever heard of amide? Functional group, right? Well, there's another amide as well. It's kind of, I reckon, a misnomer. You have an amine anion equals also an amide, because the IDE ending typically means anion. So amine anions are also called amides. Confusing, no? Yeah. Not the functional group, but the, okay. This is often called sodium amide, but it's often shortened to sodamide or sodamide. Okay, sodamide is a great base in books and on exams, okay? In practice, it's a lousy base, no good. All right, it's prehistoric, it's a terrible base. It's great on exams and in textbooks. All right? All right? I hate looking at it because it causes fires. It don't react well. I mean, it's good on the board. All right? The reason it doesn't react is because you don't want to use water or it'll just turn into hydroxide. If you use organic solvent, but it has no solubility in organic solvents. But you know what? 150 years ago, they didn't have as many choices. But for some reason, it remains in textbooks. Okay, on the board, it works beautifully. It can take the H. Of course, it'll produce ammonia. You should be doing all this right. pKa of ammonia is about 35. Which side's favored, 25 or 35? Weaker acid, right? It's favored by 10 to the 10. What's that, 10 billion? So at equilibrium, you got 10 billion of these. In the end, these bases are strong enough to deprotonate terminal alkynes and make the acetylide anions. Strong bases, though. What about hydroxide? That's a more common base. Is hydroxide strong enough to do this? That X means no. No good. Not going to happen. If it did happen, we can always show the equilibrium. If hydroxide took the H, what would we get? The acetylide anion plus what? Plus water. Right? What's pK of water? 16. This is 25. Which side's favored? 25 or 16? This side's favored. So that means once equilibrium is established, you're going to have more of which side? This. Not the anion, but the H on. And the difference is 10 to the 9. You're going to have a billion of these and only one of those. Does that sound like hydroxide is strong enough? You've got a billion molecules, and hydroxide will convert one of them to the anion. Does that sound like a good base? No. Not if you want them all converted to the anion, right? No good. These are much stronger bases. Actually, the reverse reaction is thus favored, right? Isn't it favored this way? That is, what's the reverse? If you have an acetylide anion and you treat it with water, this will take an H from water. And it will go this way, and it will produce your terminal alkyne. It's going that way. And that's the basis for the miner's helmet. Everybody look at the video? 100 years ago, back before batteries became so common in flashlights, the miners, people who wanted lights, you could light a torch and have it burning on a torch, but advances were have a little lantern that could be more controllable with a little flame. It could be handheld. Actually, some of the miners also had it on their helmets and had a little flame up there, burning up there. Don't get your hair on fire. And then you have a flame to light up where you're looking. But originally based on this reaction, calcium carbide reacted with water to make acetylene. And acetylene is a gas, often burned. You can burn the gas and create the flame. All right? Well, what is calcium carbide? Well, calcium carbide is just CaC2, but the C2 is, then you got the calcium 2+ sitting with this. It's like a double acetylite anion, right? Now, calcium carbide can be made from base compounds like calcium oxide and carbon, heated up. You know, a lot of these high temperature reactions have been done for 500 years, thousands of years before they even knew what they were doing. But this can be produced on sort of mass scale. So it was around, 100, 200, 300 years ago. But what happens if you take these carbanions and treat them in water? Well, we just showed that. The anion takes an H from water and it goes back here. So you supply the water, you get this. And this is acetylene. That's where it's H on each end. This is the simplest alkyne you can have, acetylene. It is a gas. It's used for torches these days. Anybody familiar with acetylene torches? Yeah? You've used acetylene as a torch? Yeah? Okay. But then also you're going to make hydroxide, right? Come this way, you're going to make hydroxide. The calcium can sit with that. But this reaction forms the acetylene, and so this is done. They combine the calcium carbide pellets with the water. It's 2 different chambers. It's amazing this thing doesn't just blow up. But they had a compartment, and they could light it. But I'll send you a little video about it. They control the flame. Probably the water's just dripping on the calcium carbide, and it's just producing acetylene in a small amount. And it's coming out, and it can just burn. Okay, so that's an application of the reverse reaction. But usually we'll be doing the forward reaction. We'll be making these. Now during test 3, we will react these, as I think listed at the very bottom. We'll react these as nucleophiles. And I'll say, you remember how we made the carbanions? And you guys will know. And then I'll remind you, it was on March, what's the date, 7th? Okay, at about 8:45, and that's how you make acetylite anions. And that's the end of the chemistry. We're not going to use them now. Just how to make the anions right now. That's in the material for test 2. What do we have? We have alkene reactions, and we have some alkyne reactions. Some of them are similar to the alkene reactions, but we also have a couple of new things. Tautomerization, and then we got the complete reduction of alkynes to alkanes, and then the partial reduction to either cis or trans alkenes. And then we got the deprotonation of your terminal alkynes. Alkenes typically are not deprotonated. They're not acidic enough. Remember the hybridization effect. The reason that this is somewhat stable is because these electrons are in what type of orbit? sp, 50% s. Okay? Alkenes are not that acidic, and of course your alkanes are some of the least acidic compounds around. In the end, your alkynes, this is the hydrocarbon. Okay? Your most acidic hydrocarbon is this right here, your terminal alkynes. Anything else that's more acidic is going to have like an oxygen in the molecule or a nitrogen in the molecule. Right? For just hydrocarbon, that's your most acidic hydrogen. Until you think about exceptions. Okay. We got a couple of minutes. What can we look at? Stereochemistry. Any questions? What can we look at? How are we doing on the daily questions? Daily questions. Anything there? I sent out a key to this. Are there any questions about it? Basically, you see the types of questions you're going to ultimately see on test day. I hesitate to do these because you should have been doing them on your own and asking questions. I assume you, yeah, but anybody ever sprayed for bugs around the house? Perhaps you sprayed this compound around the yard, or beautiful compound, isn't it? Nice cyclopropane ring. Question: is it E or Z? E or Z refers to alkene stereochemistry, right? E or Z? How about on this carbon? Chlorine or carbon? Chlorine, right? How about on this carbon? Carbon or H? Carbon. What is it? The same side. It's Z. How many stereoisomers possible with that compound? Well, how many stereogenic sites does it contain? This alkene is stereogenic. It's got two possibilities, E or Z. This could have been drawn as E. That would be a stereoisomer. This is, alkene is one site. Any other stereogenic sites? Yes, you've got two chiral carbons. As they're drawn generically. The actual compound that's in this bug killer stuff, I don't know if it's one enantiomer or maybe it's a mixture, I don't know. Any other stereogenic sites in the molecule? I don't think so. I see three. How many possible stereoisomers? 2 to the 3 is 8. Did you draw 8? Yeah. You could draw RR and Z, or you could draw RR and E. You could draw SS and E. You'll get 8. Any of them possibly meso? No, meso is going to have some bit of symmetry so you can come right through the molecule. I mean, where can you come right through here to have a plane of symmetry? There's not going to be. It's going to be 8. It's not going to be less than 8. You'll have 4 DO. No, maybe not 4 DO pairs. Because some of them are alkenes. Other questions on that page, though? What's your biggest trouble area? Mechanisms? Mechanism, there's a number of mechanisms in the workbook. Mechanisms, one step at a time. You look at this starting and you're like, how in the world does this happen? Don't freak out. Start with what you know. We've got an alkene and H+, we'll react it with H+. Where are you going to make cation at? Make cation. Hopefully you make it in the right spot. You'll be rewarded. You'll get to where you need to go. After you do one step, then step back, and you no longer have to look at the starting material. Now look at the cation and say, what can I do next? Guess what? It ain't going to be any freaky stuff that you've never seen before. It's going to be basic things, like carbocation rearrangements. But then do one thing, and then look at the next thing. And then do another thing. And before you know it, it's going to look like the final product. So, and then it's going, oh, I see it now. Then you do one more step, and then boom, you're done. Mechanisms are often like that. Even when there's a book of advanced mechanisms. You can get them online. They're crazy. It's like, how in the world? And you just start with step 1, and then you're like, okay, what can I do next? And then, oh, I see it now. And then, okay, so we can make last comments on Monday when we come back, test on Wednesday. You know, we got nomenclature, there will be mechanisms, there'll be predictive products, two different types of questions. Just give the product, or here's the product, but give the mechanism. Short answer, stereochemistry, you've seen all the types of questions. Have a nice break, be safe. That's it, right? We don't have lab, we don't have anything, no class?
Our lab handout.
Lab handout.